Hello students, it's Dr. Sansom here. Our quote for today comes from J. van der Waals from the Nobel Laureate Lecture, and he says it will be abundantly plain from my earlier comments that I never expected this equation, the van der Waals equation, which we're going to talk about today, to give results numerically in agreement with experiment, and yet people almost always act as though that were my opinion. And if I may be permitted to look back on the way I've come, I must confess that it may fairly be called a detour. And I wanted to share this thought with you today because I think sometimes when you think about life, it's common to have a plan for how it'll go, and you think about life happening in a straight line, and that usually doesn't happen in so many ways, including in our science careers, but usually you end up in a good place anyway. And in this case, van der Waals earned the Nobel Prize, so he ended up okay. So our learning objectives today are to talk about kinetic molecular theory. The exciting thing that's going to happen today is that we're going to kind of put together everything that we've talked about so far, all the equations that we've used, and we're now going to think about explaining why that is happening. And we're also going to talk about real gases and how they deviate from ideal gases. Just to clarify, the gases we've been talking about so far are not fake, but they are being treated as an ideal gas. So we'll talk about what that means and how that's different from what we have been talking about before. So the first thing that we're going to talk about is kinetic molecular theory. Now, all of those words matter. Kinetic has to do with movement, molecule, which is molecules, and then theory, which is something that explains a phenomenon. So kinetic molecular theory is going to explain the movement of molecules and relate that to all of these macroscopic observations that we're seeing. So the kinetic molecular theory has several sort of points to it, and these are the rules or assumptions that we make when we're talking about an ideal gas. The definition of an ideal gas is that it's going to follow these rules. So the first one is that gases are composed of molecules that are in continuous motion, traveling in straight lines and changing direction when they collide with other molecules or with the walls of a container. The molecules are negligibly small compared to the distances between them. We've talked about this a little bit before when we just introduced the idea of gases. They're compressible because there's so much distance in between the molecules. The pressure exerted by a gas in a container results from collisions between the gas molecules and the container walls. We've also talked about that a little bit. Gas molecules exert no attractive or repulsive forces on each other or the container walls. Therefore, their collisions are elastic or do not involve the loss of energy. Now, this is one of the ones that's really important when we're talking about ideal gases versus real gases. So this assumption that the molecules are not interacting with each other in terms of attractive or repulsive forces is a really important assumption for ideal gases. And finally, the average kinetic energy of the gas molecules is proportional to the Kelvin temperature of the gas. We've also talked about this. So as the temperature increases, the kinetic energy will increase. If the temperature decreases, the kinetic energy will also decrease. So these are the key ideas that we're going to be using to explain all of the things that we have talked about so far. So we'll have some time later where we're going to be looking at each of the equations and talking about this. So I want you to take a picture of this slide, these 5 points, and kind of keep this in mind in your back pocket for when we get there. Now, there's one additional thing that I want to talk about before we start talking about all of those equations, which is the root mean square speed. I mentioned this the other day. The root mean square speed is the square root of all the averaged squares of the speeds. So if we have a molecule A and it has a certain speed, we square that, and then we add the molecule B speed squared, and then we add the molecule C speed squared. We take the average of those, and then we take the square root of it. Why do we do all of this? Well, if we just took the plain average, it would be a little bit lower than the root mean square average. That'll be a little bit higher, but this will be the the speed of the molecules that have the average kinetic energy. So if we have the root mean square speed and we do 1/2 m times URMS squared, then we get the average kinetic energy for that temperature. So that's why we care about it. And essentially, this matters because when we look at molecules, they're going to have a distribution of speeds. So for example, if we look at helium, this kind of sort of like an elongated bell-shaped curve that we see here is going to tell us the speed of the molecules at a certain temperature. So in this case, all of the molecules are at the same temperature, but you'll see helium molecules having higher velocities than, say, xenon molecules. That's because the helium molecules have a lower mass, and so then they have to have a higher URMS in order to balance that out and come up with the same kinetic energy. Now, if we had the same molecule, but we increase the temperature here versus 100K, 200K, 500K, etc., then what we see is this distribution of speed sort of spreads out. We have more molecules that are moving faster. To calculate the root mean square speed, we're going to use this equation, URMS equals the square root of 3RT over m, where m is the molar mass. It has to be in kilograms because we're getting to joules here, and that's kilograms meters squared per second squared. So that'll help us get to the right units. So we use kilograms per mole for our molar mass. Temperature in Kelvin, and R is the universal gas constant that we're familiar with. This one will be the one in joules, so 8.314 joules per mole Kelvin. Okay, even if molecules have different masses, they'll have the same kinetic energy at the same temperature. But that means that if you have a heavier mass, then you're going to have a slower speed. And if you have a lower mass, you'll have a faster speed. And likewise, if the temperature goes up, the average speed will also go up. Okay, so let's do a practice problem calculating this. We have nitrogen. This is what makes up most of the gas in air. And the typical speed of a nitrogen molecule at room temperature. We want to know what the URMS is. So we're going to plug in here 3 times 8.314 joules per mole Kelvin times 298 Kelvin at room temperature, and then divided by 0.028 kilograms per mole. And then we're going to take the square root of that. So we'll end up getting 515 meters per second, which is the same as 0.32 miles per second or 1,152 miles an hour. So in other words, this is moving really fast. If this were an airplane, it would actually be above the speed of sound, supersonic. But the molecules around us are moving this fast all the time, just at room temperature. A note here that joules are kilogram meter squared per second squared, so that's how it cancels out the kilograms in our molar mass, and our meter squared per second squared, when we take the square root, is how we get our meters per second. Okay, now we're going to move into the main part of the day. We're going to be talking about each of these laws. The first law that we talked about was Amonton's or Gay-Lussac's law. P1 over T1 equals P2 over T2. Now, what I want you to do, we'll pause the video here, and I want you to talk with your group about how kinetic molecular theory explains this law. Okay, hopefully you had a good conversation about this, and hopefully you talked about temperature measuring average kinetic energy. And so when we increase the temperature, we're going to increase the kinetic energy of the molecules. If the molecules have more kinetic energy, they're going to collide more frequently with the walls of the container and with more force, and that is going to result in higher pressure in our container. Okay, next we have Boyle's law. Again, take a moment here to pause and discuss this with your group. Look at kinetic molecular theory and explain how does kinetic molecular theory explain our observation that pressure and volume are inversely proportional to each other. Okay, here, according to kinetic molecular theory, our gas particles are going to be having elastic collisions with the walls of the container. And those collisions, if we decrease the volume of the container, will happen more frequently because it's a confined space. So if I have more collisions, that's going to relate to higher pressure. So as my volume goes down, then my pressure will go up. Okay, next we have Charles' law. And again, think about how kinetic molecular theory explains this law. Okay, for Charles' law, volume and temperature are directly related. This is because if we increase the temperature, then the gas molecules will have a higher average kinetic energy. And if the pressure has to stay the same, then the volume has to increase in order to compensate for that greater energy. Next, we have Avogadro's law. Same thing, we'll pause here, take a moment to discuss this with your groups. Okay, here we have added more moles to a system, and because we've added more moles of molecules, and if it's true that the pressure has to stay constant, then the volume has to increase because there will be more collisions that are happening. And if there are more collisions that are happening, they have to happen over a larger area in order for that pressure to stay constant. Okay, we've got Dalton's law. Take a moment again to pause here and explain this one. Okay, again here, this is similar to Avogadro's law. We're adding more molecules of gas, so we're going to have more collisions occurring. And if we have a fixed volume here, then when we have more collisions occurring over the same area, that will increase the pressure. Okay, now we have Graham's law. Take a moment here to explain this one. We actually talked about this a little bit the other day. We talked about this idea that if the molecules of two different gases have the same temperature, then the average kinetic energy has to be the same. But average kinetic energy isn't the same as speed because kinetic energy is influenced by both mass and velocity. So if we have something that is heavier, then the velocity will be lower. If we have something that's lighter, that has more mass, then the velocity if something that's lighter that has less mass, then the velocity will be higher. So our light molecules will diffuse and effuse quickly, and our heavy molecules will diffuse and effuse slowly. That's because the kinetic energy is proportional to the temperature. If they're at the same temperature, the kinetic energy has to be the same, and therefore it will depend on their mass, how fast they'll be able to move. Okay. Last one we have here is Henry's law. So again, pause for a moment here and try to explain this with regard to kinetic molecular theory. Okay, for this one, when we increase the partial pressure of a gas above the surface of the liquid, that is going to increase the number of collisions with the surface of the liquid. Essentially, the surface of the liquid is like one of the walls of the container for the gas that's in that container. And so there will be more collisions with the surface of the liquid, which means that there will be more opportunity for it to stick and dissolve into the liquid. Okay, now I want you in your groups to do this practice problem. We have a spray can is used until it's empty except for the propellant gas. It has a pressure of 1344 torr at 23 degrees Celsius. If we throw it into a fire, what will the pressure be in the hot can? By the way, this is not recommended. So I want you to calculate this, and I also want you to explain what happened using kinetic molecular theory. Okay, to do this, we should use Amonton's law, or P1 over T1 equals P2 over T2. We have to remember to turn our temperatures from Celsius into Kelvin, and we should calculate 3,387 torr for the pressure of the hot can in the fire, which again is not recommended. Okay, how is this happening? Well, as we increase the temperature, the molecules are moving more quickly. The kinetic energy increases. Because they're moving around faster, they're going to collide with the walls of the container more often and with more force, and that is going to increase the pressure in the container. Okay. I want to use that as an example, just like when you have an exam and you have to explain something, you want to make sure that you walk through all of those steps. So it would be insufficient to say we increased the temperature so it increased the pressure. That's just a statement of fact, but not an explanation. So in order to explain, you have to include the detail about why increasing the temperature increases the pressure. And that's the part of kinetic molecular theory. When you increase the temperature, it increases the average kinetic energy of the molecules, which means they're moving faster, which means they're going to collide more frequently with the walls of the container. So make sure if you're doing an explanation that you include all of those links in the logic in order to actually explain something instead of just stating a fact. Okay. We're going to now talk about real gases. So everything we've been talking about so far, all the laws that we've looked at, everything has been for what we call ideal gases. And if we have an ideal gas, we're going to be neglecting attractions and repulsions between molecules, so those molecules aren't interacting with each other. And we have to also assume that the volume of the gas molecules themselves is negligible compared to the size of the container. In other words, the gas molecules are very small and very far apart from each other. Now, these assumptions work really well, but under what conditions? Is it going to be under high temperature or low temperature? This is going to work best under high temperature. So there's the weird sound effects here. I can't figure out how to get rid of them, so sorry for the weird noises. But it works best at high temperature. And that's because if we were at low temperature, then those interactions between the molecules would matter more because they'd be moving more slowly and they would see the molecules around them more. But if they're moving around very quickly, then they don't really see the other molecules. Those interactions don't matter as much. What about high pressure or low pressure? Also, I don't know if you'll be able to hear the weird there's cars beeping outside because I'm in New York. So anyway, is it going to work at high pressure or low pressure? It turns out
absolutely correct.
This will work better at low pressure. And the reason it will work better at low pressure is because at high pressure, we're going to have so many molecules that are close together that we won't be able to neglect the volume of the particles themselves. In other words, there's not as much space between the particles, and so that the size of the particles themselves is going to make a difference. If we look at sort of a diagram of this, on the left side we have the ideal gas versus the real gas. Real gases do have attractive interactions, and therefore the volume of the real gas will be slightly lower than the volume of an ideal gas because those attractive forces will pull the molecules in closer together. Likewise, if we look at an ideal gas, on the right side here, the ideal gas is going to have these elastic collisions, but in a real gas, the particles will be attracted to the other particles around them, and so the pressure of that collision will be slightly lower. So real gases would have lower volumes and pressures than ideal gases under the same conditions. So let's look at this graph. On this graph right here on the y-axis, we're plotting the ratio of the volume of the real gas over the volume of the ideal gas. So if this is above 1, it means that the real gas takes up more volume than the ideal gas, and if it's below 1, it means that the real gas takes up less volume than the ideal gas. So let's first look at hydrogen here, which is this orange line. If we look at the orange line, we know that for hydrogen, we've got two factors. This is true for all of them. We've got two factors that are going to cause problems. Either these attractive forces between the particles or the volume of the molecules themselves. Now, what about having a higher than expected ratio here? This happens when molecules are taking up space in the container. So in other words, the volume of the real gas will be slightly bigger because the molecules themselves take up some of the space, and therefore you have to have extra volume to account for the molecules themselves. So when we look at hydrogen, all we see is that top part. It doesn't ever dip below 1. And that top part where it's higher is when molecules are taking up space in the container. Notice on the x-axis here, that's at very high pressures that we're going to start to see this effect. In reality, most of our lives happen about 1 atmosphere, not 200 or 400 or 1,000 atmospheres. So under regular circumstances, this usually doesn't matter. But under high pressures, it will matter because the molecules themselves can't be compressed, only the space in between them. And so that upswing at the high pressures is going to be caused by molecules taking up space in the container. What if we look at this part that's on the left, like for CO2? Here we're having an attraction between the gas molecules, and that is making the volume of the real gas be slightly smaller than the volume of the ideal gas at these lower pressures. And this happens for all of the molecules that have intermolecular forces. Now, we haven't learned in detail about those intermolecular forces yet, but even if you just look at the molecules, you can see CO2, for example, is like the largest of these molecules, and it has the strongest intermolecular forces or attractions between particles. So these differences due to real gases, because of molecules taking up space in the container and because of attractions between the gas molecules, show up when we see the van der Waals equation, or the equation for real gases. Instead of just PV equals nRT, we're going to have two corrections here. We have a pressure correction, and this it's attached to the P in the PV of the equation. And this one is the correction for the molecular attraction. So there's a constant A that is measured for different gases. N squared is going to be the number of moles squared. And then V squared will be the volume. And then we also have a correction for the volume of the molecules, which is our B constant, and then you just multiply by the number of molecules to see how much that's going to affect the volume. So these two corrections correct the molecular attraction and the volume of molecules. If we look at the van der Waals constant for oxygen, A, it's 1.36 for oxygen, but it's 5.46 for water. So why do you think that would happen? Let's pause for a minute. We see this difference because A is a correction for molecular attraction, and water molecules are polar. Because they're polar, that means they're going to have stronger intermolecular forces between them. And we will learn more about that later on, but for now, knowing that it's polar, that means they're going to interact more strongly, so my A constant would be bigger. And if we look at constants for different gases here, we can see A constants vary a lot. They can be very small, like for helium, which we expect because it doesn't have any interactions really with anything else. It's nonpolar and it's very small, versus something like CCl4, carbon tetrachloride, which is going to have a really large A constant because it's very large. It's going to interact strongly with other molecules. And then if we look at B constants, we'll see sort of the same thing. The smallest one here is our helium. That doesn't vary dramatically between nitrogen, oxygen, CO2, etc., but then carbon tetrachloride is a lot larger. And so that is going to correct for the molecule size. So now, the last part that we've got today is on your participation worksheet, you have several problems. And what I want you to do is actually just look at the problems and decide which equation you would use. So I don't want you to actually solve them out, unless you have time to do that. But for now, I want you to just focus on choosing which law you will use. And I want you to pay attention to how you know that that's the right law for you to use. The reason we're doing this is because we've learned about all kinds of different gas laws, and now you're going to see problems and they won't necessarily be presented like, hey, this one's a combined gas law, or this is a Dalton's law problem. So you have to figure that out using the context of the problem. So I want you to practice that. This should be a discussion with your group so you can talk about why you think each of these is the way it is. Okay, I'm going to put these up here for the gas laws you should choose in these situations. It's okay if you don't know Charles or Avogadro's or Boyle's law by name, just as long as you know which equation it is you should use. And that's everything for today. Thanks, everyone.